In mathematics, the natural numbers are those used for counting and ordering. These purposes are related to the linguistic notions of cardinal and ordinal numbers, respectively. A later notion is that of a nominal number, which is used only for naming. Properties of the natural numbers related to divisibility, such as the distribution of prime numbers, are studied in number theory. Problems concerning counting and ordering, such as partition and enumeration, are studied in combinatorics. There is no universal agreement about whether to include 0 in the set of natural numbers. Today some textbooks, especially college textbooks, define the natural numbers to be the positive integers 1, 2, 3. While others, especially primary and secondary textbooks, define the term as the non-negative integers 0, 1, 2, 3. History of natural numbers and the status of 0. The most primitive method of representing a natural number is to put down a dot for each object. Later, a set of objects could be tested for equality, excess or shortage, by striking out a dot for each object in the set. The first major advance in abstraction was the use of numerals to represent numbers. This allowed systems to be developed for recording large numbers. The ancient Egyptians developed a powerful system of numerals with distinct hieroglyphs for 1, 10, and all the powers of 10 up to over 1/1,000,000. A stone carving from Karnak, dating from around 1500 BC and now at the Louvre in Paris, depicts a 276 as 2 hundreds, 7 tens, and 6 ones. And similarly for the number of 4622. The Babylonians had a place value system based essentially on the numerals for 1 and 10. A much later advance was the development of the idea that a 0 can be considered as a number, with its own numeral. The use of or 0 digit in place value notation dates back as early as 700 BC by the Babylonians, but they omitted such a digit when it would have been the last symbol in the number. The Inca and Maya civilizations used a 0 as a separate number as early as the 1st century BC, but this usage did not spread beyond Mesoamerica. The use of a numeral 0 in modern times originated with the Indian mathematician Brahmagupta in 628. However, 0 had been used as a number in the medieval computers, beginning with Dionysius Exiguus in 525, without being denoted by a numeral. Instead nulla from nullus, the Latin word for none, was employed to denote or 0 value. The first systematic study of numbers as abstractions is usually credited to the Greek philosophers Pythagoras and Archimedes. Many Greek mathematicians did not consider a 1 to be a number, so to them a 2 was the smallest number. Independent studies also occurred at around the same time in India, China, and Mesoamerica. Several set theoretical definitions of natural numbers were developed in the 19th century. With these definitions it was convenient to include a 0 as a natural number. Including a 0 is now the common convention among set theorists, logicians, and computer scientists. Many other mathematicians also include a 0, although some have kept the older tradition and take 1 to be the first natural number. The term counting number is also used to refer to the natural numbers. Likewise, some authors use the term whole number to mean a natural number including a 0. Some use it to mean a natural number excluding a 0. While others use it in a way that includes both the 0 and the negative integers, as an equivalent of the term integer. In using indices, beginning with 1 is still common, except when the beginning is a rather trivial form of the problem fittingly numbered 0. In all areas of mathematics that deal with spaces of some sort, as a rule include 0, because is the logical beginning of a series of spaces of ascending dimension. Notation: mathematicians use n to refer to the set of all natural numbers. This set is countably infinite, it is infinite but countable by definition. This is also expressed by saying that the cardinal number of the set is Aleph null. To be unambiguous about whether 0 is included or not, sometimes an index 0 is added in the former case, and a superscript or subscript is added in the latter case. Some authors who exclude 0 from the naturals may distinguish the set of non-negative integers by referring to the latter as the natural numbers with 0, whole numbers, or counting numbers, denoted W. Others use the notation P for the positive integers if there is no danger of confusing this with the prime numbers. In that case, a popular notation is to use a script P for positive integers. Set theorists often denote the set of all natural numbers including 0 by a lowercase Greek letter omega, I per mil. This stems from the identification of an ordinal number with the set of ordinals that are smaller. Moreover, adopting the von Neumann definition of ordinals and defining cardinal numbers as minimal ordinals among those with same cardinality leads to the identity. Algebraic properties. The addition and multiplication operations on natural numbers have several algebraic properties. Closure under addition and multiplication. For all natural numbers A and B, both A plus B and AA, B are natural numbers. Associativity. For all natural numbers A, B, and C, A plus equals plus C and AA, equals A, C. Commutativity. For all natural numbers A and B, A plus B equals B plus A and AA, B equals BA, A. Existence of identity elements. For every natural number A plus 0 equals A and AA, 1 equals A. Distributivity of multiplication over addition. For all natural numbers A, B, and C, AA, equals plus. No non-zero zero divisors. If A and B are natural numbers such that AA, B equals 0, then A equals 0 or B equals 0. Properties. One can recursively define an addition on the natural numbers by setting A plus 0 equals A and A plus S, B, equals S, A plus B, for all A, B. Here S should be read as successor. This turns the natural numbers into a commutative monoid with identity element as 0, the so-called free object with one generator. This monoid satisfies the cancellation property and can be embedded in a group. The smallest group containing the natural numbers is the integers. If one is defined as S, 0, then B plus 1 equals B plus S, 0, equals S, B plus 0, equals S, B. That is, B plus 1 is simply the successor of B. Analogously, given that addition has been defined, a multiplication A, can be defined via AA, 0 equals 0 and A, S, B, equals plus A. This turns into a free commutative monoid with identity element 1. A generator set for this monoid is the set of prime numbers. Addition and multiplication are compatible, which is expressed in the distribution law, AA, equals plus. These properties of addition and multiplication make the natural numbers an instance of a commutative summaring. Summarings are an algebraic generalization of the natural numbers where multiplication is not necessarily commutative. The lack of additive inverses, which is equivalent to the fact that n is not closed under subtraction, means that n is not a ring. Instead it is a summaring. If the natural numbers are taken as excluding 0, and starting at 1, the definitions of plus and A, are as above, except that they begin with A plus 1 equals S, A, and AA, 1 equals A. For the remainder of the article, juxtaposed variables such as AB indicate the product AA, B, and the standard order of operations is assumed. A total order on the natural numbers is defined by letting AA per mil currency be if and only if there exists another natural number C with A plus C equals B. This order is compatible with the arithmetical operations in the following sense: if A, B and C are natural numbers and AA per mil currency B, then A plus C A per mil currency B plus C and AC per mil currency BC. An important property of the natural numbers is that they are well-ordered. Every non-empty set of natural numbers has a least element. The rank among well-ordered sets is expressed by an ordinal number. For the natural numbers this is expressed as I per mil. While it is in general not possible to divide one natural number by another and get a natural number as a result, the procedure of division with remainder is available as a substitute. For any two natural numbers A and B with BA per mil 0 there are natural numbers Q and R such that A equals BQ plus R and R, B. The number Q is called the quotient and R is called the remainder of division of A by RB. The numbers Q and R are uniquely determined by A and B. This Euclidean division is key to several other properties, algorithms, and ideas in number theory. Generalizations. Two generalizations of natural numbers arise from the two uses, A natural number can be used to express the size of a finite set. More generally, a cardinal number is a measure for the size of a set also suitable for infinite sets. This refers to a concept of size such that if there is a bijection between two sets they have the same size. The set of natural numbers itself and any other countably infinite set has cardinality LF null. Linguistic ordinal numbers first, second, third can be assigned to the elements of a totally ordered finite set, and also to the elements of well-ordered countably infinite sets like the set of natural numbers itself. This can be generalized to ordinal numbers which describe the position of an element in a well-ordered set in general. An ordinal number is also used to describe the size of a well-ordered set, in a sense different from cardinality. If there is an order isomorphism between two well-ordered sets they have the same ordinal number. The first ordinal number that is not a natural number is expressed as. This is also the ordinal number of the set of natural numbers itself. Many well-ordered sets with cardinal number have an ordinal number greater than. The least ordinal of cardinality is. For finite well-ordered sets, there is one-to-one correspondence between ordinal and cardinal numbers. Therefore they can both be expressed by the same natural number, the number of elements of the set. This number can also be used to describe the position of an element in a larger finite, or an infinite, sequence. Hypernatural numbers are part of a non-standard model of arithmetic due to Skillum. Other generalizations are discussed in the article on numbers. Formal definitions. Historically, the precise mathematical definition of the natural numbers developed with some difficulty. The Peano Axioms state conditions that any successful definition must satisfy. Certain constructions show that, given set theory, models of the Peano postulates must exist. Peano Axioms. The Peano Axioms give a formal theory of which the natural numbers may serve as a model. The axioms are, there is a specific number, which here will be called the first number. Every number has a number as its successor, denoted by S, A. Intuitively, S, A, is a +1. There is no number whose successor is the first number. S is injective, that is distinct numbers have distinct successors. If A permel B, then S, A permel S, B. If a property is possessed by the first number and also by the successor of every number that possesses this property, then it is possessed by all numbers. The first number in the above definition need not correspond to the number 0. All systems that satisfy these axioms are elementarily equivalent in first-order logic. However, there exist models for the Peano axioms that are uncountable. These are called non-standard models for arithmetic and are guaranteed by the upward-la paragraph in Heimer-Skillum theorem. The namia 0, or 1 is typically used for the first element, but the set of integers greater than any chosen integer satisfy the axioms. In Peano's original formulation, the first number was denoted a 1. Constructions based on set theory, a standard construction in set theory, a special case of the von Neumann ordinal construction, is to define the natural numbers as follows: set 0 equals a, the empty set, and define S, A, equals AAA for every set A. S, A, is the successor of A, and S is called the successor function. By the axiom of infinity, there exists a set which contains 0 and is closed under the successor function. Then the intersection of all inductive sets is defined to be the set of natural numbers. It can be checked that the set of natural numbers satisfies the Peano axioms. Each natural number is then equal to the set of all natural numbers less than it, so that 0 equals a, 1 equals 0 equals a, 2 equals 0, 1 equals 0, 0 equals a, 3 equals 0, 1, 2 equals 0, 0, 0, 0 equals a, n equals 0, 1, 2. Now 2, now 1 equals 0, 1, 2. Now 2, and now 1 equals now 1 equals s, now 1. And so on. When a natural number is used as a set, this is typically what is meant. Under this definition, there are exactly n elements in the set n, and n a permel currency M if and only if n is a subset of M. Also, with this definition, different possible interpretations of notations like Rn coincide. Even if one does not accept the axiom of infinity and therefore cannot accept that the set of all natural numbers exists, it is still possible to define what it means to be one of these sets. For a set n to be a natural number means that it is either a zero or a successor, and each of its elements is either a zero or the successor of another of its elements. Other constructions, although the standard construction is useful, it is not the only possible construction. For example, one could define 0 equals a, and a equals a, producing 0 equals a, 1 equals 0 equals a, 2 equals 1 equals a, etc. Each natural number is then equal to the set of the natural number preceding it. It is also possible to define 0 equals a, and a equals a, producing 0 equals a, 1 equals a, 0 equals a, 2 equals a, 0, 1, etc. The oldest and most classical set-theoretic definition of the natural numbers is the definition commonly ascribed to Frege and Russell, under which each concrete natural number n is defined as the set of all sets with n elements. This may appear circular, but can be made rigorous with care. Define 0 as a and define a as xa y xa section ya permil x. Thena 0 will be the set of all sets with 0 elements, 1 equals 0, will be the set of all sets with 1 element, 2 equals 1, will be the set of all sets with 2 elements, and so forth. The set of all natural numbers can be defined as the intersection of all sets containing the 0 as an element and closed under S. One could also define finite independently of the notion of natural number, and then define natural numbers as equivalence classes of finite sets under the equivalence relation of equivalence. This definition does not work in the usual systems of axiomatic set theory because the collections involved are too large. But it does work in new foundations and in some systems of type theory. See also: canonical representation of a positive integer, countable set, integer, number classification of numbers for other number systems, notes. References: Landor, Edmund. Foundations of Analysis. Chelsea Pub Company. ISBN A0-8218-2693-X. Dedekind, Richard. Essays on the Theory of Numbers. Dover. ISBN A0-486-21010-3. Dedekind, Richard. Essays on the Theory of Numbers. Kessinger Publishing, LLC. ISBN A0-548-08985-XA. N. L. Carruthers, Real Analysis, Cambridge University Press, 2000, ISBN 0-521-49756-6. Brian S. Thompson, Judith B. Bruckner, Andrew M. Bruckner. Elementary Real Analysis, ClassicalRealAnalysis.com, 2000, ISBN 0-13-019075-6. Von Neumann, Johann, Zur Einfuhrung der Trashfinanzelen, Acta Literarum Accientiarum Rajni Universitatis Hungarici Francisco Joseph Sectio Scientiarum Mathematicarum 1, 199 €208. Von Neumann, John, 1923, On the Introduction of Transfinite Numbers, in Jean van Heijgenut, From Frege to Gar Paragraph Del, A Source Book in Mathematical Logic, 1879-1931, Harvard University Press, ppA 346 €354, ISBN A0-674-32449-. 8. English translation of von Neumann 1923. External links: Haswinkel, Michiel, ed., Natural Number, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Axioms and Construction of Natural Numbers, Essays on the Theory of Numbers by Richard Dedekind at Project Gutenberg, Weierstein, Eric W., Natural Number, MathWorld.